Okay. Should I walk through it? Mark?
I think I'm good, thank you.
Okay. And somebody asked for 16. Is that what I also heard? Okay. 16, I noticed immediately that I saw, I have a cosine and a sine. I have a function and its derivative. So that told me that I should be using a substitution. And then I have a nice, pretty little trig. And then it becomes an arctangent problem. Okay. I don't think I was recording when I posted all of the answers. So if you'll bear with me, wherever the heck I just put it. I'm just going to show them in case anybody who's not here right now needs to see them. That's number 2. It's number 4. Six go. Number 6. Number 8. Number 10 was tricky. I did it probably differently than other people would have. And that gives me this weird set of answers because you can write it in multiple ways. That's number 10. Here was number 12. We just did 14 and 16. And here is 18. Okay. In case, I'll be posting this video in case anybody needs to see it. Okay. So today we're going to be using or reviewing an old tool. Who remembers how to do that? Yeah, that's what I thought. Okay. All right. So the whole idea here is that we're taking a polynomial and we're turning it into a perfect square. So let's take a look at what perfect squares look like. All right. So if I have a perfect square, it's and you know I've just got this constant here, whatever that is, and I square it out, I'm going to get this polynomial looking thing. Now, what the whole idea behind completing the square is that we're going to take something that is not like this or like that, and we're going to turn some of it into something that does look like this. So let's do an example and let me show you what I mean. So if I have x squared plus 10x minus 3. Okay, this is not a perfect square because this, first of all, a squared is not, negative 3 is not a perfect square. So this isn't going to work for me. So here's the deal. I cheat. I turn this expression into an equation. Okay. This is a lie. But the idea is that whatever this thing is, it's equal to something, and I'm just going to call it y. And at the end of the day, I'm going to rearrange this thing, and I'm going to have y out again. And what it's equal to is what this guy is equal to. Okay? So the way we do this is I take the 3 and I bring it on over to the other side. Now, I leave this space here for a reason. Because what I need to do is I need to add an a squared term in right here. But the problem is that I don't know what a squared is. But if I look at this term, that 2a, oh, that's 2ax, sorry. Oops, there's an x right there. This 2a has to be equal to that 10. So that means a is 5. So that means I'm going to add a 5 squared, because it's a squared on both sides. Now, here's the important thing that I want to point out. I really, really, really want you to write it in parentheses. And I'm going to show you why on the next example, why that pair of parentheses can save your butt. Okay? So now, if we look at this carefully, I've got x squared, a squared, 2 times a times x, which means I've got this shape. And that means I can turn this shape into that shape, which means this is true. Now, I'm going to just clean all that up. And now I move the 28 back over to get y alone so that I have an expression again. And these two things are the same. Now, let's point out for just a hot second, this, if I were to graph it, is a parabola, right? This is a parabola also. It's the same parabola, but this is in vertex form. This has a vertical shift of negative 28 and a horizontal shift of left 5. Okay, so these two are the same. They're just the parabola written in different ways. Does that make sense? Okay, so let's do a couple more examples. All right, I need that sheet. Don't throw that one away yet. So let's do x squared minus 12x plus 4. So the thing here is to set it equal to y, move the 4 over, now take this middle term and divide it by 2. So we get negative 6. Now, here's why the parentheses is a big deal. Because if you forget the parentheses and you just write 36, you're going to lose that negative sign most of the time. And that's what I don't want you to do. Over here on the right-hand side, I don't care. It doesn't matter. Over here, it matters. Here I can just write 36. Done. Poof. Finished. And now, and bring it on over. How's that feel? Okay. Kevin, you with me today? Okay.
Yeah, I was having some like internet problems and computer problems because like it wouldn't turn on, and yeah.
All right. Well,
but I managed to work it.
Right. Were you present enough to see this problem done?
I was present to hear you start the second one. I mean the first one. Sorry.
Okay. So hopefully your internet is better and we can continue from here. Okay. Let's all practice one more, just to say that we could. Let's do one that's fun. So try this one on your own. move the 3, set it equal to y, move the 3, divide the middle term by 2, square it on both sides, complete the square, and then move the term back. Okay, so we're going to set it equal to y. And we're going to add -5/2. And this side, I'm just going to square it and call it 25/4. So now I have x minus 5/2, y minus 12/4 plus 25/4. And then combine my like terms and move it on over. And I get minus 13/4. And we're done. How'd it go? Cool. Awesome. Fantastic. All right. So we're moving along in a pretty good clip. Now, let's do a hard one, okay? Or one that's got more bells and whistles. So now, here's the kicker. We got this 3 out in front. And when we were messing around in the very beginning of all of this, this was the formula. It didn't have a constant other than 1 out in front here, okay? So what we need to do is we need to get that 3 out of here. It can't be part of the problem right now. So we basically do what we did before. But now I got to divide everybody by 3 so that I have what's called a monic polynomial. Monic meaning mono, meaning having the first term is 1. It doesn't have a leading coefficient. Okay, and now we can complete the square. So I add -4 squared, and I'm just going to say 16, but 16 over 3 is 48/3. Okay. Just because I didn't want to write another step. I'm kind of being lazy about that. And so now I can combine, I can write it out as x minus 4 is equal to y plus 44/3. Now I can move stuff back. And we're done. It's not equal to anything. It's an expression as before. Okay. How did that work out? Okay, great. Now, who cares? Good question. The reason why it matters is because we can do stuff like this. Well, taking a look at that, I can't do a U sub. It doesn't factor, okay? There's really nothing I can do with it right now except complete the square, okay? So if I complete the square, and now I'm going to add 3 squared to both sides. Now I get x plus 3 squared, and this is -8, so it comes on over as +8. And that's what this guy is equal to. So now if I look at it now, Now I have a nice function that looks a lot like a trig. Which trig does that look like?
Arctangent?
Yeah, the arctangent. The arctangent is a plus, and it doesn't have a square most of the time. A square root, I mean, you know. So now we're going to say and now we have now we can do our trig with it. So I'm going to do the cosine. Cosine of theta is equal to, and I'm going to square it just to get rid of it all. It'll be 8 all over x plus 3 squared plus 8. And the tangent of theta is x plus 3 all over the square root of 8. And so the secant squared of theta d theta is equal to 1 all over the square root of 8 dx. So dx is equal to square root of 8 secant squared theta d theta. And now plugging all of my stuff in, I need an 8 and a 1/8. And my dx becomes the square root of 8 secant squared theta d theta. So secant squared, cosine squared cancel, square root of 8 comes out. That reduces actually and now I have the arctangent of x plus 3 all over the square root of, or 2 square roots of 2. And now it's the square root of 8, which is, to heck with it, 1 all over the 2 square roots of 2. And you're done, plus c. How is that? How are we doing on the trig sub? Show me fingers, scale of 1 to 5. 5 being awesome, 1 being I don't even know what that means. All right, good. Beautiful. Better than HL1 is doing. Oops, that was out loud. Okay, let's try one a little different maybe. Okay, this one's not bad. You want to try that one on your own? Okay, so here when I completed the square, because I looked at that and I said, well, you know, I mean, I just x squared plus 2x plus 1 would be a perfect square. Well, I can just steal a 1 out of this guy, and now I've got my perfect square. So sometimes you can make that, you can just pull it out of that term, especially if it's positive and you're looking for something positive. It's nice to be able to just steal it when you can. And then you don't really need to do a u sub. You could have just jumped right to an arctangent, but if you say that this is my u, your du and u, and then you arctangent it and pull it back out. Who got it? Okay, good, good. Okay, awesome. So I think what I'm going to do is I'm going to call it at that. We'll end class a little bit early. I'll be sending out a homework assignment. It'll just be like these. It'll be complete the square and then you do the trig. They won't be too bad. They'll be kind of normal looking. And in the meantime, take it easy. Have a good day. See ya.